Yes, okay. Thank you very much. It's a pleasure to be here. I think I have to take care a little bit. So I'll talk about reconstructions of the large-scale structure. And the first thing I want to mention is that when we analyze data from galaxy surveys, we essentially look at the statistics. For instance, the 2-point or the 3-point statistics. We can measure correlation functions, for instance, by throwing sticks of different sizes and see whether there is a particular preferred scale. And it's quite surprising that, as you know, we find an excess at about 150 megaparsec. So spheres of about 490 million light years have an excess probability of finding galaxies. And you know this comes from the CMB, this comes from when the time when light was coupled to matter. Now, as it has been already explained, they help us as standard rulers, and those are pretty big scales. If you want to be robust in your statistical analysis, you don't want to reduce the volume of your survey. You want to exploit all of it. And that's a problem, because you just have one realization. Okay? It's not the same as if you study galaxy evolution and you look at all the galaxies you have at different redshifts. You can do statistics and your universe has made a lot of experiments for you. But in this case, there are not that many, right? And one very important thing is that the whole endpoint statistics, 2-point, 3-point, 4-point, etc., fully characterizes the probability distribution function of your tracer, the tracer of your underlying dark matter field. Now, your underlying dark matter field has evolved cosmologically, and it's nonlinear, highly nonlinear, and this makes things more complicated. I hope we get back to the slides. Okay, sorry, thank you. Maybe I was talking too much. So, okay. So, what is important is how are you doing your analysis? You use the 2-point statistics to extract cosmological parameters, to extract baryon-acoustic oscillations, redshift space distortions, primordial non-Gaussianities, deviations from general relativity, even neutrino masses. You use the 3-point statistics now more recently, also to measure baryon-acoustic oscillations, also to constrain redshift space distortions and primordial non-Gaussianities. And of course, the 3-point statistics tells you a lot about gravity, and there are degeneracies you can only break when you take into account both of them. Here I have a sketch of how you throw triangles into the volume, and you see how likely it is that it connects different tracers. Now, it should be equivalent to do it in configuration space or in Fourier space, but at the end it's not, because you're looking at a particular range of scales and it's not equivalent at the end of the day. And in that sense, there are different methods in both spaces. And the error bars are constrained by the covariance matrices, by 4-point statistics. So you want to make sure you have those under control. Now, as you know, those baryon-acoustic oscillations have been measured first in the CMB, in the multipoles. Then here you see how they have been measured with galaxy redshift surveys in Fourier space and in configuration space. In configuration space, you see the scale, about 105 megaparsec per h. So if you divide by h, then you get something larger. But in any case, you see different tracers at different redshifts, and you see a very clear detection, about 9 sigma detection of the BOs. Now, how do you put those error bars because you have an experiment which has been done only once. So you have to make sure that you can do that experiment in your computer and that you have control over it. And I will talk about that. And then you see it in the Lyman Alpha First, also less than 10 years ago. Here you see galaxies from the Bosch survey. It looks pretty homogeneous. Okay, now what is reconstruction? Because this is what I'm talking about. It's essentially a nonlinear transformation. And usually in our context, many times people, when they refer to reconstruction, they mean undoing the effects of gravity. So by having some time machine where you take structures back in time and you manage to recover a more spherical baryon acoustic oscillation, more spherical spheres. You see here a cut through the sphere. This is a nice sketch done by Nikhil Padmanabhan, and you see how the nonlinear structure formation deforms those spheres, and it can take away 5 sigma detection in the BOs. So what is going on when we do BO reconstruction, and why is it so useful to apply reconstruction for BOs, as it was proposed by Daniel Eisenstein in 2007? Well, the reason is that you linearize, you Gaussianize the distribution of your tracers. And that has been mathematically shown by Marcel Smithfull in 2015. You're carrying information from the higher order statistics to the 2-point statistics. So you make your analysis in your 2-point statistics and you see a larger detection. And it's important to understand this because this is telling us that if you make a proper higher order statistics, you can analysis, you can avoid doing reconstruction, okay? But at the time being, for the time being, it's very practical and it's very useful and we are doing it. But here you see how other studies emerge. The first BO detection with the 3-point statistics was actually by Gaztañaga, but very low sigma detection, and you start to see really robust detections with Zachary Slepian in 2018, and then very recent developments, not only by Héctor Gilmarín, but by others as well, going to the 4-point statistics. Another kind of reconstruction is reconstructing the void distribution. And one has to be very careful again, because when you reconstruct cosmic voids from galaxies, those are not observables. The observable is the galaxy distribution. Eventually, you will be able to substitute all your analysis with a higher order statistics analysis. Now, this is the first BO detection with cosmic voids, and we defined cosmic voids in a robust way which should not depend on cosmology. Now, what we did here with a code developed by Cheng Zhao in 2016 called DIVE was to find the Delaunay triangulation, which, so in 2 dimensions, a Delaunay triangulation defines a circle. In 3 dimensions, it's actually tetrahedra. And then you find quartets of galaxies, you define empty spheres, and the centers of those empty spheres can be defined as the center of your cosmic void. Now the problem is that if you consider very small radii, then you're essentially finding groups of galaxies. So that's the only thing you have to make a cut and say, above about 15 megaparsec radii, I will consider all cosmic voids I find, and then you get to this. What you're doing here is, again, doing some physical transformation, nonlinear transformation, to push information from the higher order statistics to the 2-point statistics. In particular, what you're doing is you're recovering the negative tail of the Gaussian distribution. Because when you do reconstruction of the galaxies for BO reconstruction, you're linearizing, Gaussianizing the positive tail of the Gaussian density distribution, because galaxies preferentially reside in high density regions or higher density regions than average. That's the reason. It's rare to find galaxies in voids. Now, that is why the statistics you can find by performing this Delaunay triangulation. By the way, if you connect the centers of the Delaunay triangulations, you obtain the Voronoi tessellations. Now, what I want to stress is that this is a nonlinear transformation. And as it had been already seen by Patrick MacDonald in an appendix in 2000, and later on in 2012 by Euroceliac in a very dedicated paper, very generally, but focused on the Lyman alpha forest, when you have a nonlinear transformation of a tracer which suffers redshift space distortions, what you end up is with a bias in the redshift space distortions. So it's very dangerous to make a redshift space distortions analysis with anything which has suffered that nonlinear transformation. And there could also be other biases. So we wrote a paper on this, and we found that in a very robust way. However, using this void reconstruction as I have presented is very useful to combine it with the galaxy distribution and obtain the tightest constraints in BOs so far. And those have been done by combining both data sets. So what we did here in several papers led by Cheng Zhao was to combine both data sets, and it happens that, as expected, cosmic voids are anti-correlated with galaxies, and the BO is anti-correlated. So the way of combining them needs a weighting factor which is negative. So here you see different, if we take 0, we are not going, well, this is 0.1, this is 0, this is essentially saying we don't take the cosmic void, so we see the 2-point correlation function of the galaxies for the BOSS survey, and you see here the nice BO, but you can see how this BO becomes much sharper, up to 20% sharper, which is a huge gain. Of course, then, why should we be interested in reconstruction? Well, you can use all these tight constraints to constrain, for instance, the equation of state of dark energy, as it was shown in this nice paper led by Gombo Zhao. You can also use it to constrain primordial non-Gaussianities. The idea of this is that when you're studying primordial non-Gaussianities, deviations from Gaussianity in the initial conditions to constrain the different inflation models, what happens is that you're contaminated by the non-Gaussian contribution caused by gravity, by nonlinear structure formation. You can get rid of that by applying reconstruction. And I should stress in all these things that we have applied simple inverse Seldovich reconstruction. I will explain in a minute what that is about. But this is kind of the most simple thing you can do, and it's super powerful. Again, we gain a lot if in FNL, this second order deviation in the potential from Gaussianity. We gain a lot of detection significance after reconstruction. So in the bispectrum, in the 3-point statistics in Fourier space, we showed that this helps a lot. Now, I have said that the basic reconstruction algorithm has been used, and it seems to be successful. Now the question is, are all problems solved? And the answer is essentially not. Now there is a lot going on between inverse methods, because I haven't explained it, and I should come to this later on, but the way people reconstruct this is essentially by smoothing the galaxy distribution, applying a filter on it, applying then just a linear bias to it, dividing by that linear bias, and then you take that as a proxy of the dark matter density field. You compute with linear theory the velocity field, and you go back in time. And you can't go back in time too much. You usually go back to redshift 3 or so, and then you gain 5 sigma detection in the BO. That helps already. That was essentially what I was showing. Now, inverse methods versus forward modeling. Now, there's a lot going on in forward modeling, Bayesian methods, which are based on posterior sampling or in the maximum a posteriori, or in machine learning. This is not maximum likelihood, this is machine learning when I write that. This is also emerging as a potential method, not yet applied to data, and full density map information versus the endpoint correlation functions. Then we have, there's a lot going on precisely in this forward modeling by having efficient gravitational evolution, not only Viscosity and body simulations, but based on Lagrangian perturbation theory, particle mesh codes, or machine learning again. Peculiar velocities have to be modeled, the galaxy bias has to be modeled, systematics, and regarding systematics, there's a huge problem with angular completeness. And then we need to compute robust covariance matrices to determine, and in a robust way, those signatures of the large-scale structure. There is a very interesting thing going on because the analysis of the cosmological large-scale structure poses a big challenge. It calls for joint study of theoretical models because those, as you have seen in previous lectures, determine the cosmology. Then numerical methods, because complex nonlinear systems as the ones we are facing require those. And also data analysis methods to deal with survey strategy and selection effects, which at the end of the day end up with all these radial selection, angular selection, and so on. And then coping with huge volumes with vast amount of data. Now with, there is DESI going on, Euclid, Foremost, JPass, Weave. There are so many galaxy surveys going on which will trace very close to our Hubble horizon. I mean, we are going to go to Redshift 5 without any problem. And then, of course, with SKA and so on, we'll go beyond that. Lyman alpha first, lensing, quasars, luminous red galaxies, emission line galaxies, etc. So this calls for big data techniques with effective models. Okay. What's going on? Oh, it was already. So the question is, why not simulate the galaxy distribution with all known physics for cosmological large-scale structure analysis? And the answer to this is that they are very expensive. Best current simulations cover at most 300 megaparsec per inch cube volumes, such as Illustris, TNG Eagle simulations, and so on. And they're not flexible with the Halo galaxy connection, as they have to make a choice of the astrophysical models, feedback processes, star formation, and so on. Once you get the data and you have to analyze that, you want to be flexible and you want to adapt your mocks to the data to trust your error bars. And that's why they are also not very practical, although, of course, we all rely on them to understand the physics which is going on. So it's complementary, but it's not the main tool we use in cosmological large-scale structure analysis. Now, can we perform dark matter-only simulations and connect the dark matter halo to the galaxy distribution, which would be less costly? The answer is yes, and this is what we are doing routinely. You can do it with semi-analytic models. You can do it with halo occupation distribution, statistical models, or with halo abundance matching or sub-halo abundance matching methods. So where you essentially connect halos, if you resolve structures and even substructures to galaxies, and you usually introduce a scatter to get the statistics right and so on. And the reason why you can do this is because there is a tight relation between the circular velocities in galaxies and the dark matter in central regions of galaxies. And because of this tight relation, you can do that. However, they are still too expensive. Largest simulations with necessary resolution for emission line galaxies, for instance, cover 2 gigaparsec per inch cube volumes. If you are interested in bright galaxies, for instance, then and you want to go to 10 to the 7 solar masses halos, resolve them, then the largest simulations are about 1 gigaparsec cube volumes. So this is very interesting and important and necessary to understand how they are distributed, but they do not help us to compute covariance matrices, because we can do at most one or a few, and even with volumes which are far smaller than the ones we are going to observe, which is crazy. So we need effective models and a probabilistic framework. Okay, let us recall my first slide. A model is accurate if it accurately reproduces the statistics used for the cosmological analysis. So I don't care much about how you construct your model if at the end of the day, the error bars are indistinguishable from super heavy calculations. And that is the basis to use machine learning and other kind of techniques. So about effective structure formation model. Yeah, this is something I want to talk about now. And there is a lecture here where I have provided to you, and it explains everything in detail, because I'm gonna go a little bit fast with it. But I want to present you an effective equation to model the large-scale structure, okay? So from first principles. So let us start with a Hamiltonian system and a distribution function, which depends on positions, velocities. It could be momenta, but okay, I have taken out the masses. At this moment, you can assume all have equal masses, and time. The total number of particles will be the integral over all that phase space, okay? Nothing new to you. And the total continuous changes to the phase space of the system can be written in this way. This is poor math, nothing. This is not an equation, really. It's not equal to anything yet. Now, due to Liouville's theorem and the fact that probability should be conserved of this distribution function, we can write a continuity equation for the phase space. This means for a continuity equation for this flux J, which includes derivatives of positions and momenta, essentially, okay? And when you work this out, you can find the different terms, and all this is equal to 0, because this is a continuity equation you can write down. Now, however, if you include here Hamiltonian's equations of motions, then you find out that there are several terms which are cancelled out. And then you end up with this being equal to 0, if we are considering only continuous changes. Of course, if you have discontinuous changes, you get the general expression of the Boltzmann equation, but equal to 0 in this case. Now, you can introduce some convenient definitions, the mean number density as the integral over the velocities of this distribution function, the density when you weight them with the mass, the moments when you weight them also additionally with the velocity to some power, and the velocity field would be just with I equal to 1, okay? That would be the mean velocity field, okay? This shouldn't be anything new to you. Now, the thing is, of course, the different moments will lead to the continuity equation or to Euler equation, okay? And if you want to see the details how you get there, you can look at those notes I have provided to you, but essentially, the trick is that the integral of the when you have a distribution function and you make the integral at minus infinity and infinity, say, at the limits, then that has to go to 0 because the probability distribution function has to be normalized. It cannot explode. And then you get rid of certain terms and you end up with the usual known continuity equation and with this Euler equation. And now I want you to pay attention to this term here, which I have defined because I started with this, but then this I have converted it into these two terms by defining the difference between the mean velocity field and the velocity of each particle. So you could call that the random or the peculiar motion, okay? Now this is gonna be key. What happens now is that you can further simplify Euler's equation by taking the continuity equation, and then you can model try to model this tensor. This tensor, which is the of these random motions, if you want. So essentially, in our case study, this will model the virialized motions. And you can find that there is a pressure and there is a stress tensor. This is a way to model it, and you can even go and say, I want to model it with the linear elastic model, and then you find this expression. This is very common. And you get, essentially, you can substitute this term here with all this term, which I have modeled here. And here you can see exactly why. It's very easy to see why these terms look like that if you write it down with indices. And as I said, it's in detail in those notes. In any case, what I want you to take away is that this guy here will model the highly nonlinear structure formation. Now, what we usually do here is to do a transformation to co-moving coordinates, take into account the proper velocity. So here's the peculiar velocity here. And that transformation transforms gradients with respect to r, with respect to the co-moving coordinate x. You get a 1 over a scale factor, and the time derivative is transformed too. This is the usual thing which surprises one when one studies cosmology. But in the lecture notes I have added, it's very precisely derived. And now you introduce also conformal time. By introducing all this and Poisson's equation, you end up with this equation here, which, if you take the linear elastic model, is expanded into these terms. And this is the equation I want you to look at. This is the general structure formation, effective structure formation equation you would consider in cosmology large-scale structure modeling. Now, what happens is you usually get rid of this term, which, where does it come from? From those random motions, we called it, right? That tensor. Usually get rid of this, and then if you get rid of this, then you can perform Eulerian perturbation theory. If you additionally consider that this is like the total derivative with respect to a Lagrangian, right? Then the co-moving derivative here, and you write everything as a dv d tau, merging those two terms, then you can perform Lagrangian perturbation theory. Okay? Now, if you recover this term, you can do more things. And things become more complicated. But the other things, already Lagrangian and Eulerian perturbation theories can be complicated. Here is a simulation within second-order Lagrangian perturbation theory as introduced by Buchert and Ehlers 93. I mean, I did this simulation now on my laptop, right? 512 cube, 100 megaparsec per h. It's used today to set up initial conditions for embodied simulations, but not going to redshift 0, where you see there's a lot of shell crossing because that term is missing. Okay? And it's still used in some codes to do fast mock catalogs. Now, this is what I introduced 9 years ago, augmented Lagrangian perturbation theory, combining Buchert and Ehlers formalism with Bernardot formalism, which uses excursion set plus Eulerian perturbation theory for the spherical collapse model. And this is still being used. And as you see, there is an improvement in the resolution. But now we are modeling this term, and we get this. And this looks pretty much like an n-body simulation already. Actually, we are within we are within 1%, sorry. Within 1% up to k equals 0.5, and we are above 90% cross-correlated at k equal 1. Okay, I wanted to show you this, and then I want to show what we do, because we have now we modeled the large-scale structure, and now what do you do? How do you, I was talking about this requirement or necessity of modeling introducing effective models. So here, essentially, this is extracted or inspired by the work of MacDonald and Roy 2009, where Pat MacDonald not only introduces a Taylor expansion of the local density field, but also a non-local expansion. Here, for instance, this is the first non-local second-order term. Here you have non-local third-order terms. And here you would have more other terms. Here you have a short-range non-local term, which depends on delta. This was actually introduced by Peacock and Heavens in the 80s. And then here you have terms which depend on the velocity. Now, you can model these things. You can model these things in an effective way and find the basis in Eulerian space, which connects the halo distribution with your large-scale cosmic web. And when you do that, you start finding results which resemble within seconds what you would get with n-body simulations, and where you get the 2-point and the 3-point statistics right. And here I must stress the great work by Andrés Balaguer Antolinez, who is sorrowfully a little bit sick today. But I want to mention the state of the art in the field. I mean, I'm happy that it's happening here, but this is the state of the art. We are achieving up to the Nyquist frequency within 1% accuracy in the 2-point statistics, and look at the variance of the power spectra. And this is compared to a set of about 100 n-body simulations, high-resolution n-body simulations, which are good enough for emission line galaxies. You see, they are on top. Also, the error bars, which is what I was caring about, right? At the beginning. Now, what happens? This doesn't work. I have to wait. Doesn't react. No, I don't think so. So what I'm showing here is how we compare with the halo distribution. I didn't show yet properties of the halo distribution, and I didn't show how it compares with models of the galaxy distribution. And that's what I wanted to show now. And, well, we can skip it. It looks very good. No, I'm joking. Let's see what happens. Okay. Maybe I can force to quit. Forzar salida. Vista previa. Forzar salida. Forzar salida. Pumba. And then I go here. Sorry for that. I could have thought about this. This is the typical thing. Reinitiate, right? Well, these are the halos, but now Andrés is looking at properties. He's looking carefully at so that you can make arbitrary mass cuts and still get the statistics right. And when I show this P0 means including redshift space distortions, and this is very important because data are with redshift space distortions. And this is the quadrupole and the hexadecapole, and you can see the incredible agreement with halos from a simulation compared with halos from a simulation. Please tell me this still works. Ah, yes. And this is how it compares with galaxies. For the whole population, it's doing a very good job up to k equals 0.3, which is the expected range where we want to do the analysis. But of course, there's still room for improvement, and there are still things, deviations at higher k modes, and as long as the theoretical models become better and better, we enlarge the K range in which we do analysis. So it is important. Now, this is the last part of my presentation, and it's about Bayesian inference. And again, there's another link to another lecture if you want to know more about information theory, for instance. Here, I just want to stress that Bayes' theorem, and because I was talking about a probabilistic framework, the Bayesian framework is a good choice in this case. And here we can write the posterior of a signal we want to measure, conditioned on some data and some prior knowledge, as the product of a prior and a likelihood. The prior represents our notion of the signal we want to recover. And the likelihood represents the data model and how they are related to the underlying signal. And then we have the evidence, which is the data model, which permits model comparison. And well, the Bayesian information is encoded also in the choice of the probability distribution functions. And Bayes' theorem represents a learning algorithm which can be updated. Once you get more data, you can use your posterior as a new prior, okay? So, all right. So about how would you then do a Bayesian inference analysis? You start defining the prior, then the likelihood, or then the link between the prior and the likelihood. Then you apply Bayes' theorem, which is essentially expressing the product of both. And then you can do several things. You can compute the evidence. There are several things to do that. And make model comparison. You can find the maximum of the resulting posterior, and then you get the maximum a posteriori. For instance, Euroceliac's team is applying this in a very efficient way, even using particle mesh codes to recover the large-scale structure from observations. You can sample the posterior within Markov chain Monte Carlo, other kind of improved methods like Hamiltonian Monte Carlo. And then once the posterior has been sampled, you can compute different moments, like, for instance, the mean expected moments. And just let me show you how this works. You can define, for instance, a potential energy as minus the logarithm of the posterior. And then you can try to find the maxima by just doing the partial derivative of with respect to your signal and equating this to 0. That is the equation you want to solve. And that, by different choices, you can solve that. Now, if you want to sample the whole probability distribution function, you need some random fiducial variable, and you introduce that within Hamiltonian Monte Carlo sampling, within a Hamiltonian sampler, by adding a kinetic term. And that kinetic term is expressed here as usual. Now this mass, this Hamiltonian mass, is like a preconditioner. If you set it to 1, it's the least informative thing you could do, but you could insert there, for instance, the survey geometry, the radial selection function. We did that in our work, and we managed to show an improvement in the efficiency of 70% for the Hamiltonian sampler, for instance. Now, this kinetic term has a nice thing, because we have expressed everything as minus logarithm, right? So if you take exponential of minus of this, it is essential and not normalized Gaussian, okay? So it's just a Gaussian multivariate. We know how to sample that. That's easy. And here I can express the joint probability distribution of the signals, which would be the positions and the momenta. And if you express that and you take this Hamiltonian, then you find that they can be expressed as multiplications, and it's super easy to marginalize over them, because you just have to randomly sample new momenta in each iteration and forget about the previous ones. And that's the way how you marginalize, and you end up sampling just the posterior distribution function you're interested in. So this is how Hamiltonian Monte Carlo allows you to sample arbitrary non-Gaussian distribution functions. What you have to do is to evolve the system, the Hamiltonian system, and these Hamiltonian equations have to be discretized. And this is the usual discretization, the leapfrog scheme. But we showed that when you go to 10 million dimensions or larger, higher order discretizations start to become necessary, or at least some very large improvements, because otherwise you need thousands of iterations just to burn the chain. And with this higher order, you can be at 512 cube, and within 30 iterations or so, it converges. And by the way, I have a collab I will show in a minute where there is an exercise for you, for all of you, and it's prepared and it shows this. Now, because we are with numerical methods, Hamiltonian energy is not conserved, although it should. And that's why you have to introduce a metropolis hasting step to ensure that you're not accepting wrong values and getting off the global extrema, right? Well, and this is how it works, and different groups have implemented it. And this is a solution to multi-streaming as opposed to inverse approaches, because when you have, for instance, say 2 tracers which have peculiar velocities and they encounter each other at a particular low redshift, and you are observing those, and then you smooth that and you want to go back in time, you actually can't, because you have shell crossing. They have, at the same position, different velocities, right? But with forward models, you can solve that. And you can manage to get reconstructions like this of the large-scale structure based on real data. In this case, you can do a lot of things. Yes, this is a recent work we did with a new code, Bayesian code, which includes cosmic evolution, which I coded. It's this one, birth, and it has been applied to high redshift data to find protoclusters and so on. Now, about the exercise in Colab. So, yes, let me see. Okay, here it is. So I have this exercise, and I have essentially written down in Python everything as I would write it down in C++, because I didn't want to use Python libraries, then you don't see anything, right? But here you see really what's going on, and it doesn't use much external software. So here, for instance, Poisson equation, say. Right? Poisson equation, if I go to Fourier space, then I can write it down. Well, I will skip the vectors, but let me say I would have IKR phi k, right? And then if I do the gradient derivative with respect to r, I will get this ik, right? And if I do it twice, I will get it twice. So I get ik vector times ik vector, which gives minus k squared. So then I can say, okay, this is easy to solve in Fourier space. For k being different than 0, it's just this. And all these things are explicitly coded here. So it's a little bit long, but here how you defined k-space, hermiticity, how you compute the power spectrum, and so on. Even Lagrangian and Eulerian perturbation theory is coded in a way where you end up, and also the Hamiltonian Monte Carlo sampler is coded. And then when you run it, okay, here we start running it. You first have a 3D Gaussian realization. This is a Gaussian field. And then I wanted just to show you a high resolution simulation with Lagrangian perturbation theory. So you see the cosmic web. And then I go to large volumes of 1,250. I show the power spectrum. This is the underlying theoretical power spectrum, and this is the power spectrum of the Gaussian realization. You have it here. And please look at this, and this. There's like an X here. Focus on that. This is aliasing, okay? It loses power because there's an aliasing by taking the particles and performing a mesh. But you see again this X, right? Now things are sharper because you have done cosmic evolution. By the way, to redshift 0.5, and with a very similar, essentially with the same number density as the BOSS survey. I wanted to have it realistic. And with a nonlinear bias model, you get this bias tracer. So you see it's very off, and it looks like this. This is the discrete realization. And then you run the sampler. And the first iteration already gives you a Gaussian density field, but the power is very off. Well, you run it, and you start seeing how it magically converges. And this is by applying nonlinear models. And ending up with something which is pretty close to what it should be. Let me see. Yeah, you see we get very close to what it should be. And maybe you can see the X. You see it, but it's a Gaussian. Well, that's the exercise. And let me see, I think I don't have much more. Yeah, that was it. That was my last slide. So thank you very much.
Yeah, thank you for your talk. So I'm interested in your model to approximate a halo clustering by using the biasing model. And you call the BAM model. Yeah, and so in a naive impression, I thought that it would be rather difficult to produce the approximate halo power spectrum by only using the bias expansion.
No, it's okay. Okay, I was not very explicit in that. Sorry. We look at the bias expansion, and we know from the theory that we need to get it right at least up to third order non-local bias. You can, with Eulerian perturbation theory, you can mathematically show that the leading terms are just up to third order. This is done by Patrick MacDonald, 2009. So you want to make sure, and it happens that we found in that paper the link to the description of the cosmic web. So the cosmic web, I don't know if you know about this, but you compute the tidal field tensor, and then you look where, for instance, all the eigenvalues of the tidal field tensor are positive, and then that's a collapsing region. Where they are all negative, that is an expanding region, like a void. And then you look at different combinations, and you find that essentially, mathematically, you find that all that description of the cosmic web goes to third order. Now, we found that link, and then we use the invariance of the tidal field tensor as the variables in our learning approach, where we extract the complex bias model from n-body simulation. So we need at least one big n-body simulation to extract that bias. And then we can map it, because we can do those computations very fast. So we are not explicitly using the perturbation theory bias expansion. We are indirectly using it by providing the terms it needs, the dependencies.
So you extract especially bias value, so for each bias operators from the simulations, and you use some density field from the simulations.
No.
No.
We use our fast approximative gravity models. That's how we
okay.
gain a lot.
Yeah.
And we do low resolution. We just do 3.9 megaparsec per inch, like 4 megaparsec per inch resolution cells. And then we know how to sample them. And then we have subgrid models. Because then inside that cell, they are not randomly distributed. We have to know how to distribute them.
Yeah.
It's a little bit complex, like for another discussion, private maybe or
okay.
something.
Okay. Thank you very much.
Thank you very much for your interest and your question.
Thank you for the very interesting talk. If I understand correctly, you mentioned that the first step is to apply a smooth of the galaxy distribution.
No.
No?
No, that's old inverse methods. But that is already working super well. That's what I showed at the beginning. Standard BO reconstruction just does that. Yeah, I can show you. It's a little bit more complicated because you have to take into account a peculiar velocity term. But it does the job from 4 sigma 5-ish to 9 sigma detection of the BO. No, what I was talking about at the end are forward model. That's you get completely different results, much more detailed. They are much more expensive.
Okay. Okay, thank you.
Sorry.
Okay, thanks for the talk and the exercise. Could you please explain again the problem with redshift space distortion with voids?
Oh, yes. It's whatever it's not only with cosmic voids. It happens also with the Lyman alpha forest. Whatever nonlinear transformation is applied, and in the case of the Lyman alpha forest is essentially the exponential of minus tau, the optical depth. And the optical depth is the variable which suffers redshift space distortions, not the flux directly. So there is a nonlinear transformation in between, and that introduces a bias into the redshift space distortion term, into the Kaiser factor. So this is something we derived for cosmic voids in a paper, in a Physical Review D paper, Albert Chung and myself. Well, actually, the derivation was myself with Pat McDonald, and Albert did all the calculations, even with observations, finding the great match. So the great match doesn't mean we have it under control. It just means we found the bias. And whenever you have a bias, it's a problem.
Yeah, I'm a bit, I don't know if I understood very well this term that you add for modeling the peculiar velocities. So basically, what I understood is you have Seldovic or whatever perturbation theory, and then you add this model, and then that describes the virialized regions, and then you have a way better description.
So the last thing.
My question would be, because I didn't know about this, but for example, I know that for Seldovic, to push it a bit more, you add these advection models to basically to keep the already once shell-crossed regions there and not like passing through.
Yeah,
so
there is
the question would be how does it compare to your results?
The adhesion model. The adhesion model is essentially Berger's equation, and Berger's equation is very expensive to solve. There is one limit in which it's less expensive, which is when the adhesion, the viscosity parameter goes to 0, but is not 0, but goes towards 0. And there you get the skeleton of the cosmic web. And that is something you can compute with when you compute the convex hull. And there is a work by Johan Hidding and by the group of Riem van der Weijgert, essentially with Shandarin, about this. And I'm working with them as well on these things, but it's still expensive. What I have shown here is a completely new model. I cannot tell you what it does. because it's unpublished, but it does it within just 4 times or so more being more expensive. Already with one additional step, it improves a lot.
Okay, so it improves
Well, it improves the. In my case, I care about ALPT because, to my knowledge, it's the most accurate approximate method, which correlates best, and it improves a lot the augmented Lagrangian perturbation theory model. Yeah.
Hello, thank you for your talk. I want curiosity. You told about the machine learning. Could you tell us one problem that was solved with it using machine learning? And in these people that work in this machine learning, show the equation or something else or to describe, or they use only see black box?
Well, this is has not been applied yet ever to observations. That's one problem with people dedicated to machine learning in cosmology. They have to find the first application. But what I can tell you is numbers. For instance, to reach a precision of within 1% up to k equals 0.5 in resembling an n-body simulation, what they do is they start with the Zeldovich approximation, and then they learn how to correct the Zeldovich approximation with 1,000 n-body simulations, 1,000 expensive n-body simulations, and then they have a cost function, which is essentially, if I have it right, the square difference of, or the Euclidean distance, if you want, of the displacement field of the n-body simulation with respect to the one they get. But there are other works, also just with number counts, and still none of them are as accurate as ours. And ours is not really, it's you can look at it as from the machine learning point of view, but everything is coded. Like the code BAM are like 80,000 lines of code. We are not using any package from machine learning or whatever. But it can be expressed as a machine learning because we learn a kernel, which we apply to the density field, and then we apply the bias, which we extract. Okay.
Okay, thank you.
Thank you very much.
Thank you everyone for the discussion. Okay, so we have a coffee break, and then we're back, please, on time, because we have a very intensive. Yeah.
Actually, they come a few minutes so that we tell them how to get ready, because
Yes.
next session is going to be intense.
Yeah.
And we really have to make it on time. So we shall be very strict in terms of the times assigned to each speaker. So we'd like you to be ready at the time sharp. So maybe if you come a few minutes earlier, and then we tell you how the procedure goes.
Yeah, we are thinking of using the laptop of the organization, if you don't mind. So we go faster, unless there is anyone who is, really have slides with beautiful, very beautiful, extremely beautiful animations you want to show us. We encourage you to use this laptop. And yes, so, okay, that's all. Enjoy, yeah. signal when you have 2 minutes left, okay?
So at 6 minutes, you tell me.
7 and plus 2
Plus 2.
plus 1.
Work? Yes, perfect. Hi everyone, my name is Veva. I am a PhD student at the University of Geneva, and I'm very grateful to have the opportunity to present my work here. So what I'm presenting today is based on a recent paper that I wrote together with my supervisor, Camille Bonvin, and Nastasia Grimm, who is a postdoc in our group. So the objective of my PhD is to constrain gravity modifications using the large-scale structure of our universe. So in order to do this, I'm interested in looking at the universe on very large scales. And on these large scales, it is possible to describe the universe in the context of cosmological scalar perturbation theory. And we already saw this morning, actually, during the dark energy lecture. There are 4 key ingredients that allow us to do this, which are 4 fields, which you can see here. So we have 2 fields related to the matter content of the universe. So we have a density fluctuation, a velocity field. And then we have 2 gravitational potentials that describe the geometry of space-time. So we have a spatial component and a time component. So general relativity provides us with some fundamental relations that relate these 4 quantities. So first of all, in GR, we have that the 2 potentials are equal to each other. We then have the continuity equation, the Poisson equation, and the Euler equation, which encodes the so-called weak equivalence principle, which essentially tells us that all bodies, regardless of their composition, fall in the same way inside gravitational potentials. Now, I told you before that in my PhD, I'm interested in looking at gravity modifications. So gravity modifications change these relations, and first of all, one can introduce a difference between the 2 components of the gravitational potential, which corresponds to the anisotropic stress that was mentioned in the class this morning. And then the Poisson equation can also be modified, and by convention, it is usually rewritten in a way to relate the density fluctuation not to the spatial component, but to the time component of the gravitational potential. And then the modifications are encoded in a phenomenological way in an additional parameter, which I call mu, and it corresponds to the factor y that Luca was showing us this morning. So this is a very generic modification that does not necessarily correspond to a specific theory. It's not necessarily Hornetsky, for example. But I take it as a generic modification that just depends on scale and on redshift. So this is the standard setup that is usually employed to constrain gravity modifications based on galaxy surveys. However, these standard constraints actually rely on a very strong assumption, which is that both baryonic matter and dark matter obey the weak equivalence principle. And while we have strong observational evidence at the scale of the solar system that baryons do obey the weak equivalence principle, we do not have a strong observational constraint that tells us that dark matter obeys it on cosmological scales. So in our study, we raise the legitimate question of what happens if dark matter breaks the weak equivalence principle. And again, we consider very general modifications, which we parameterize in terms of 2 modifications. So we have a parameter theta that encodes friction acting on dark matter. And then we have a parameter gamma, which parameterizes a 5th force. So how do we constrain these parameters with observations? So I told you before that I'm considering galaxy surveys. And what is typically done in galaxy surveys is to measure fluctuations in the galaxy number counts, which is this quantity here that depends on redshift and on the direction of observation n. And at leading order, these fluctuations are dominated by 2 contributions. So we have the dark matter density, which is related to the galaxy distribution via a bias B. And then we have the effect of redshift space distortions, which arises from the fact that galaxies have peculiar velocities on top of the velocity that is dictated by the expansion of the universe. So how do we obtain this quantity starting from observations of galaxies? What is typically done is to compress the information contained in here into the two-point correlation function in configuration space, which is defined in this way, and it essentially gives us a statistical measure of the probability of finding galaxies in pixels separated by a given distance d. And this quantity is extracted from observations and then can be compared with theoretical predictions. So in my case, I will compare it against my gravity modifications. So as a first step in our study, we employed this type of formalism applied to data from the Sloan Digital Sky Survey to, first of all, constrain just the parameter mu that modifies the Poisson equation. And here is what we obtain. So here we're still assuming that dark matter obeys the weak equivalence principle. And you can see that we obtain a very tight constraint. However, when we drop this assumption, so we have our parameters theta and gamma, you can see that something very strange happens, which is that our parameter mu becomes fully degenerate with the parameter gamma. So we cannot constrain mu alone anymore. And the constraints are worsened by a factor 30. And on top of this, this additional combined parameter becomes fully degenerate with our parameter theta 0. So when we reach this point, we ask ourselves, is there a way to somehow save these constraints? And the answer is actually yes, because there is what we finally call the deus ex machina, because it's literally like a divinity coming from the sky, and as in ancient Greek theater plays, it saves our situation, it saves our constraints. And this deus ex machina is a new observable, which is the effect of gravitational redshift, which occurs when we have galaxies that are sitting at the bottom of gravitational potentials. And thus, when they emit photons, these photons will lose energy in climbing out of the gravitational potential and will thus be redshifted. So you can see here the theoretical expression for this potential, which is directly related to the potential psi. So this effect will provide us with a way to directly measure this potential, and so it will give us a way to directly probe the Euler equation. So unfortunately, as of today, we do not have the possibility of extracting this signal from current surveys because this signal is much smaller than redshift space distortions. However, future surveys like DAISY and the square kilometer array will be able to measure it with a good signal to noise. So we performed Fisher forecasts for the square kilometer array and DAISY, and here I'm showing the results for the square kilometer array, including gravitational redshift. And you can see that in this configuration, we do not anymore observe the strong degeneracy between mu and gamma, but we can constrain our parameters individually and we recover tight constraints. So I leave you with my take-home messages here, and I'm happy to take any questions.
Beautiful talk. Questions? One question? Yeah. Anybody? Luca.
Thanks for the very nice and clear talk. I'm always curious about how many hidden or not hidden assumptions are there. For instance, do you have to take something about the power spectrum, the slope of the power spectrum, the background evolution?
So here, for now, we have fixed the background cosmological parameters. One can, in principle, leave them free. So that's one assumption. Then one has to introduce assumptions, for example, from the point of view of the galaxy bias. So here we are assuming a linear galaxy bias, and we use, for example, for SKI a fitting function, and we let this free. Another assumption, for example, comes from the magnification bias effect, and in this case, we fix this, and we assume, since in order to observe these relativistic effects, we have to consider two different galaxy populations. And in splitting our galaxy population in two, we consider some flux threshold that is fixed. So this is another assumption. In principle, one, in order to make this measurement, let's say, fully general, one would need to also let the parameters related to the magnification bias free, but here we fix them. So let's say there are all these parameters related to our observable that enter. And then, of course, another strong assumption is the time evolution of these parameters. So here I was showing the constraints on mu, for example, on the value today. and we assume that these parameters evolve with omega lambda, so with dark energy density. And of course, this is an assumption. We don't know that. So what one could do would be to instead try to measure this parameter in redshift bins to have a more general, let's say, approach. But here we were more interested in a proof of concept. We can discuss more later.
Yes, please discuss later.
Thanks for your question.
Sorry about that. Okay,
Thanks.
Thanks. Who is next? Is Adrian?
Can you hear me? So, hi to everyone. My name is Adrián Gutiérrez. I am a first-year PhD student at the IFT. Thank you, the organizers, for letting me present my work. And I will talk about primordial non-Gaussianity and their imprints in the large-scale structure. So, first things first, what are primordial non-Gaussianities? So, the most standard model for structure formation states that the initial conditions for the universe were seeded during inflation. The most standard model for inflation, the single field slow roll inflation, predicts that these perturbations has a spectrum which is nearly Gaussian. And hence, any violation of one of these two conditions may lead to some degree of deviation from this Gaussianity, which is parameterized in the term FNL. So here I show you two simulations, one with Gaussian initial conditions and one with non-Gaussian initial conditions. You can try to guess which one is which. Well, I guess this one was the Gaussian one, and this one is the non-Gaussian one, and here I show you the difference between both the density fields. So what are the imprints of this primordial non-Gaussianity? In the following, I will only consider the local type of primordial non-Gaussianities, which this type induces a modification on the primordial gravitational field, which can be parameterized as this expression, where phi j is the Gaussian part, and this is the amplitude of this primordial non-Gaussianity. And this has three main effects. On one hand, we modify the probability density function of these perturbations, as you can see in this plot, and this enhances or suppresses, depending on the sign of FNL, the formation of very massive structures. Of course, since you have a non-Gaussian PDF, this will induce a correlation in the 3-point functions, which can be parameterized in this way. And finally, maybe the most interesting one, is that they induce a scale dependence in the galaxy bias. The current tightest constraints, as have been introduced in the talks of this morning, came from the Planck collaboration measuring the bias spectrum, the 3-point correlation function, and leads to these constraints. But we cannot distinguish between zero or non-zero FNL. So, and these measurements are fundamentally limited by cosmic variance, so we do not expect to improve too much using the CMB. The other alternative is using the large-scale structure of the universe, using these maps of galaxies and natural hydrogen that will be done by these surveys. And these have been done with the effect of the scale-dependent bias, and this is the current constraints, but we expect that in the following years we can improve up to sigma FNL order 1 in DESI and Euclid and so on. So going back, I told you that this primordial non-Gaussianity enhance or suppress, depending on on the FNL, on the sign of FNL, the formation of these high massive structures. This can be thought or can be seen in the press sector formalism, where you introduce your Gaussian distribution, but this time you have no longer a Gaussian distribution. This time it has this form. And the modification of this mass function is shown in this plot for the both two simulations I have shown in the first slides. And as have been introduced in the large-scale structure talks, galaxies are biased tracers of the underlying matter distribution. This means that we can relate the density field of galaxies with the density field of the matter through a bias relation. In the paper by Dalal, he showed that the primordial non-Gaussianity induced a scale dependence because of this term, which scales with k squared. And this is, in this plot, I show you which kind of effect we expect to measure if there is any primordial non-Gaussianities at all. However, as you might have noticed, these B phi and FNL parameters are fully degenerated. So if we want to measure this FNL parameter, we need to put we need to know this B phi, or at least have a very strong priors. So assuming the peak background split theory, you can derive this relation between B phi and B1, but it has shown that this is no valid for some type of tracers. So in this context, we run the unit PNG or PNG unit simulations with the objectives of measuring this B phi and have simulations with primordial non-Gaussianities to validate the analysis pipeline for these galaxy surveys. There are two dark matter-only simulations with Gaussian and non-Gaussian initial conditions and fixed and matched initial conditions, which leads to an effective volume of around 70 gigaparsec cube. In addition, we run 200 fast PM realizations to estimate the variances. So the main idea is by fixing the FNL parameter, we want to measure B1 and P simultaneously, and this is what I showed you in this plot. For estimating these error bars, we have used these fast PM realizations. However, the mass definitions between the full body and the fast PM realizations are not the same, so we have applied a clustering matching. I don't know if you can see the faint lines here in this plot, which are the realization of fast PM, and in these strong lines are the unit simulations. And finally, we also have used the matching between the Gaussian simulation and the non-Gaussian simulation, because if you have a measurement that favors a higher value of FNL in the Gaussian simulation, this also appears in the non-Gaussian simulation. So you can use this correlation to get a better estimation, not only on the FNL parameter, but also in the P or B phi parameter. And this is what I show in this plot. For dark matter halos, we saw in blue using the standard error bars, in orange using the error bars derived from the fast PM, and in green using the correlations. The next step is apply this same pipeline for the other tracers as quasars and LRGs. And finally, I let you with these take-home messages. Thank you.
Thank you very much, Adrian. Any questions? One question.
I have two actually, but very quick. The first one is this FNL degenerate with the relativistic effects? And the second one is that you said in the beginning that we will be sensitive, hopefully, to FNL equal 1 or so. Then why did you use FNL plus minus 100? Haven't you checked with lower values as well? What happens?
For the first question about the general relativistic effects, we are not considering those simulations, and I think that there are quite similar effects, but I think that it occurs in different scales. So maybe you can distinguish this FNL from that relativistic effects. And with respect from the higher FNL value of these simulations, we choose this high value to get a higher signal-to-noise ratio in this analysis pipeline. But in fact, you can use it a very more realistic value, around 10 or something like that. And with respect to the surveys, they are assuming this FNL value of this B5 parameter in order to get that estimate. There are some questions about that, because a higher value of this B5 leads to a tighter constraint, so tighter forecast for this constraint on FNL. So they assuming this universality relation for that.
Thank you.
Thank you.
Okay, this works. So, hi everyone, I'm Francisco Mayon. I'm a PhD student in the Donosti International Physics Center. And today I'm going to be presenting this work that I have done concerning the statistics of bias tracers in variance suppressed simulations. So let me give a very brief introduction. So, well, simulations are extremely useful in cosmology to simulate different dark matter models or very complex procedures, for example, galaxy formation, or the nonlinear formation of structures in dark matter simulations. And in the particular case of this work, they are extremely useful for this model that we have built inside of our group that uses fully nonlinear simulations to build models for galaxy clustering that are actually able to extend into the nonlinear regime here, into values of k which are larger here of around 0.5 or 0.6. So, well, okay, simulations are very nice, but they of course have their own issues. So the main issue is that they are noisy. So in large scale, simulations are going to have a lot of statistical noise due to the fact that they are finite, and therefore the large scale modes are sampled only a few times. So one way to actually overcome this issue is to use what are called the variance suppression methods. So in this talk I'm going to focus mostly on this one, which was introduced by Angulo and Pontzen, which is usually referred to as fixing and pairing. So what is that, and how we suppress variance in simulations using that? So the first part of this procedure is usually called fixing. So to generate initial conditions for a simulation, what we usually do is that we sample the amplitudes of these modes from a Rayleigh distribution, and the phase is uniformly between 0 and 2 pi. This is what's illustrated here. This is the sampling. This is the initial power spectrum, the sampling, and then after evolution. But instead of doing that, we fix the amplitudes directly to the square root of the power spectrum, and then we sample the phases. And you can see here that what's really useful about this is that the power spectrum of the initial conditions are exactly the theoretical input. Of course, this is going to destroy the Gaussianity of these initial conditions, but you can see that even after evolution, many of these very nice statistical properties are still conserved. This power spectrum is much more regular. Okay, so the second step of this is, let's say we have a simulation A, which was generated with these initial conditions. We generate a second set of simulation, which has the exact inverted initial conditions in a certain way. So you can see that here on a region where simulation A has a very large void, simulation B has a huge cluster. So what you can imagine is that we hope the endpoint functions that we compute are also going to be their deviations from the ensemble average will also be inverted one with respect to another. So when we average over them, they will converge to the ensemble average much faster. Okay, so what we want to know is whether these procedures can actually help us make these models that we build from numerical simulations more precise. So let me talk a bit more about this model. So the idea is that we have these dark matter only simulations, and we can actually express the galaxies as biased tracers of the dark matter density field. And this means that the galaxy power spectrum can be written as a linear combination of these bias parameters here, which will fit to any population of bias tracers we want to describe, multiplied by these auto and cross power spectra of all of these fields here computed from our dark matter only simulations. So if we want to make this model, galaxy power spectrum, very precise, we want to analyze what is the variance of these auto and cross power spectra in these n-body simulations that we impose these variance suppression methods. Okay, so we do this first numerically. So we run an ensemble of 200 COLA simulations, which are just approximate n-body, first with Gaussian initial conditions, and then with fixing and pairing. And so the first thing that I want to look at is, since these initial conditions are non-Gaussian now, I want to look if these power spectra are biased, as this would be a possibility. But I'm just going to show you a very quick answer to that. They are not, so that's very nice. So let's look at this case, which is much more interesting. What is the variance suppression for these power spectra? So we can see 3 different cases here. So for the linear power spectra, so essentially this 1,1 is just the matter power spectrum of our simulations, but it has a bit of a different nomenclature. And you can see that it has a very large suppression in the variance due to fixing, and still some variance suppression due to pairing. And you can see that the same is true for the other linear power spectra. Then for the cross correlations between the linear squared, fixing doesn't do anything and pairing really reduces them. And then for the squared, none of them actually do any particular effect. So we actually also analyzed this analytically, but I won't have time to tell you much about that. But using perturbation theory and computing these auto and cross power spectra, we can identify in the structure of these calculations why this happens. But more interesting, we can use this formalism to compute their variances of these power spectra in these new fixed and paired simulations. And using this, we can combine these variances with the bias parameters to actually know what is the noise in our model for the galaxy power spectra. So this is very useful because let's say we want to model Euclid, for example, which has this volume. We would need, if we were to build this model from usual simulations, we would have to run at least a simulation as large as that to have the error in our model under control and beneath the error in Euclid. But since we have fixing and pairing, you can see here that we can have simulations as small as essentially 2 gigaparsec cubed, so 10 times smaller than the volume that we're actually trying to model. And this is already enough to have essentially the error in our model coming from these numerical simulations under control. Of course, this depends a bit on the values of the biases that we use, but still, this is already a huge gain with respect to usual methods. And so just my take-home message is that fixing and pairing greatly eases the task of building these models based on n-body simulations. And it also, we have developed a robust way to know a priori what's the effect of this method on any endpoint function and to compute their variances. So that's it.
Thank you, Francisco. Just in time. One question for Francisco. There you go.
So many of us are using this technique, and I think many of us thought about improving it, but none of us managed yet. Are you exploring improvements, like say not only pairing with 180 degrees, but pairing, multiple realizations and things like that?
Yes, so we have spent quite some time exploring different things. Mainly, essentially, as you can see here, these are the problematic spectra, right? They are the ones that essentially we would like to reduce their variances to have a really, really precise model. We have tried many of these combinations with different phases. Essentially, they don't work, and in my paper, I actually explain and prove why none of them can work. with this analytical formalism. We have done a numerical procedure where we essentially do a minimization to find an optimal phase field for which these variances are extremely suppressed. So we actually kind of brute force this problem, and we find essentially such a phase field. I didn't have time to talk about it much, but that's one way in which we could do it. We did it in such a way that it's a very fast procedure, and you could actually think about doing it to generate initial conditions for your actual n-body runs, in which the variance of some particular observable would be extremely suppressed. Yeah.
Hola, hi. ¿Cómo funciona? Well, hi, I'm Elena. I'm a second year PhD student here at the IAC. So I am doing my thesis with Ariana Di Cintio and Robert Grant. Today I'm going to talk a bit about what I'm doing in my thesis, the impact of AGN in a Aurora dwarf galaxy. Okay. I wanted to start introducing this relation, the stellar dual mass relation. This is what observational studies. Oh, I don't know how this works. Okay, this is what observational studies show about the relation between the stellar masses and its halo for the galaxies. The red line in both cases are the relation that the theoretical say that we should have, but as you see in observational, there is like this lack of stellar masses for the low and the more massive range. So in order to explain this lack, the common view is that you have two kinds of feedback. In the low mass range, we have the supernova feedback, who is expelling the gas away from the center, and this way reducing the star formation. But if we go to the higher massive, we have the supernova feedback is not efficient enough to reduce this star formation, and we need the effect of the supernova, the effect of a supermassive black hole, which introduce the AGN feedback to quench all this galaxy. So, however, there is several recent studies that says the AGN feedback could be also important in dwarf galaxy. And the ratio between dwarf galaxy that host the AGN could be larger than previously expected. So in my thesis, we take a theoretical approach to these observational studies, and we make use of simulation. In particular, we make use of the galaxy formation model of the Auriga project, which introduce magnetic fields and radiative cooling, supernova feedback, black hole growth, and AGN feedback. So, in my thesis, I make use, in order to see how important is this AGN feedback for dwarf galaxy, I used like a sample of 12 dwarf galaxy. But this 12 dwarf galaxy was run twice with the Auriga project. Once with the whole galaxy model, and once without the presence of the black hole. So if we now take a look into the sample who host AGN, we can see here my sample. We see how the relation related with the mass of the black hole, the observational relation, my sample followed quite well this observational relation. So, as you see, each point is colored and number, by the mass of the black hole. So H0 is the one with the largest black hole, then H1, H2, until H11, who is the one with the smallest black hole. Now, in order to know if there is a difference between AGN and no-AGN configuration, we compare both configurations. So here we have, again, the stellar-to-LO mass relation, but now with my sample. So you can see the cross points are the configuration with the AGN linked with its own galaxy without the presence of the black hole. You can see how there is a pattern in which the configuration without black hole tends to have higher stellar masses, and also the ones who have more difference between configuration are the ones who have larger black hole masses. Now, this plot shows the ratio between the median star formation rate through the whole times for both configurations versus the black hole mass at the present ratio. You can see how there is a pattern, and those galaxies who have the massive black hole show a larger difference in the star formation history. So those who have larger black hole masses are more quenched. Now I am going to look into those galaxies who have a smaller black hole and those who have a largest black hole. So for those who have the smaller black hole, you can see how, for example, this one, the red line is the configuration with the AGN, and the blue line is the configuration without AGN. You can see how here also in the black line, the evolution of the black hole mass through the time. So there is not much difference between both configurations. But what happens if we go for the galaxy with a larger black hole? Well, we have here a huge difference when the black hole starts. So this configuration who don't have the black hole have a larger star formation rate. That means that the black hole are quenching the galaxy. If we also look into the kinetics properties of both configurations, we have here the velocity line of sight and the dispersion maps, and also the isodensities for each galaxy. So we can see how the galaxy with AGN are slow rotator and also less dense. This is my future prospect. As I only have one set, I want to rerun all the galaxy, changing supernova parameter to have more statistics, to know if this is only related with the AGN or not. I want also increase the resolution of all my galaxy, implement another AGN scheme, and make use of another code with the same initial condition. So that's pretty much that I wanted to say. So thank you. If you want.
Okay, one question from Mateo.
So if I can, so the first question is that whether or not this AGN feedback, either mechanical or thermal, can affect the density profile of dwarfs. Maybe it refers to the third point there. And another question that I have, I guess that you put the black hole as seeds, right? At some point, the simulation of mass, maybe 10 to the 3, something like that. Have you checked whether your results are stable if you change this number to another number? Because this is quite, an important input, and it's quite, I believe it's going to affect a bit the results. Yes, thank you.
Okay, thank you for this question. The first one, I did look into the density profile of the galaxy and looking between resolution. So I have difference, and the one without AGN seems to have more density, but it's inside the non-resolution range. So I have to increase the resolution to make sure about this difference or not, because I I don't want to be sure about that because we have all the resolution limitation. And the second one, yes, I also think about that. I am running this higher resolution, but I didn't change the seed, the mask seed. But this is why I want to change and make use of another simulation to see if I use the same initial condition with another codes, I still have the same difference.
It's not working? No. So I am David Figueruelo from the University of Salamanca. I am a PhD student in the Gracchus group there in the University of Salamanca. I am going to speak about what I have been done in the last 3-4 years of my thesis. So everyone here knows that the lambda cold dark matter model is a very, very good model. It's able to fit most of our data set, but it's not perfect. We know that there are a lot of problems from the very, very fundamental level, the cosmological constant problem or the coincidence problem, the formation of a structure, this missing satellite problem, the cubes versus core problem, or the cosmological tension, for example, the H naught and the sigma tension that here are from 2 nice papers that I take these plots. So as it is not perfect, in cosmology, we try to search for an alternative that can some kind of alleviate the tension or alleviate the problem we have here in the previous problem. And in our opinion, an appealing alternative model to the lambda cold dark matter model must be something that must be very close to lambda cold dark matter because we know it works very well. So that means a minimum modification to the already known scenario. This modification should have some kind of motivation because you can put everything there and just put into class or put into one body code. It will be nice, but you need something to add this because otherwise it's just adding things. And maybe for solving the sigma tension, some late time mechanism that can erase a structure, so you can alleviate the tension between the very early universal measurement, for example, the CMB, and the late time, like Sunyal-Seldovich or other one. For example, also the H naught tension can be alleviated with some extra radiation, but there are questions on that. So here is when momentum transfer, especially in my case, the covariantized Thomson, dark Thomson-like scattering, can say something. This kind of model are based on a non-conservation of the stress energy tensor of dark Canary, and this MI is dark matter, or it could be baryon, could be both. And then the global stress energy tensor of dark matter and dark Canary will be conserved. So the idea is that the coupling will be as the relative velocity between both interacting fluid. For example, let's say dark Canary and dark matter, and here is the coupling constant that can depend on time or scale. And the beauty of this kind of model is that this model that does not modify anything rather than the Euler equation. So you have the same background as in the standard model, you have the same continuity equation, but you have a new term that if you look at this is very, very, very close to Thomson scattering. That's why the name came. It's the same term, different time evolution, but the same term that you have in baryon's equation or in photon's equation for the Thomson scattering. So just to say a bit the scale of this kind of model, for very large scale there is no modification. Both fluids have the same velocity, so the interaction just vanishes. Intermediate scale, you have a very similar process, a competition between the pressure of dark Canary and the gravity trying to cluster because of dark matter or baryons. And for small scale regime, we don't know, and body simulation are now ongoing. And regarding the time scales, if you use this kind of very, very, very simple with a constant alpha, this interaction will be efficient in the late universe, so it will be very, very useful for the sigma tension. There are kind of motivating this, a CPL-like parameterization, SIP symmetries. Well, it's not important now. So the main effects are, for example, in the power spectrum, if this works, you see that with Redshift, it's not working very well, but with Redshift, you have a suppression in the power spectrum, depending on the value of this alpha that I showed you before. This is for the case of dark energy interacting dark matter. This is for the case of dark energy baryons. And very, very important, the shift of the peak of the power spectrum. This is very, very important because usually this peak is set by the quality time between dark energy and, between matter and radiation. But here, we do not modify this background quantity, so it will be the same, but it's not. Also, for the velocity, there is a very, very similar effect at this acoustic oscillation, but now we call it dark acoustic oscillation that appear depending on the value of alpha, and for a different scale. So we are able to distinguish between the baryon acoustic oscillation and this dark acoustic oscillation. And the way of explaining that is the same as with baryons. The competition between gravity and pressure. In this case, pressure is because of dark energy. So we put this model into data. This is with a lot of data set. I don't know if you can look, but this is Planck with Bayo, Planck with supernova and Bayo, and with Sunyal-Seldovich. And unless you add Sunyal-Seldovich, you have no detection. You have only an upper limit. Once you add Sunyal-Seldovich, you have a more than 3 sigma detection. This is Sunyal-Seldovich from Planck. This is for the case of dark energy and dark matter. The very same for the case of dark energy and baryons. And this is for the tension. This is the alpha cold dark matter is the model I presented before, but letting free the number of effective degrees of freedom and effective. And B cold dark matter is a very similar model, but instead of having dark energy interacting dark matter, you have a dark radiation added to the equation. So because of that, it can be useful for the H naught, but it's very, very similar to that. So the important column is that one. Even if we do not add, this is alpha, this is the model I presented before, this is the other with dark radiation, this is the lambda cold dark matter, and this is all the different data set. Even if we do not add this Sunyal-Seldovich data, that might be problematic in some sense, we are able to have a lower value compared to the lambda cold dark matter, so this, and this, especially for this alpha cold dark matter model, that is the one I presented before. When we add Sunyal-Seldovich data, we're able to perfectly elevate the tension. In fact, you cannot combine Sunyal-Seldovich data with Planck data because they are in tension, but if you use this model, you can combine them. And for the H naught tension, this alpha cold dark matter model, as we are just the same background, there is no possibility of elevating the tension of H naught. We have only larger errors, but we cannot elevate the tension. The other model that is very similar, but with this dark radiation instead of dark energy, can elevate in some sense the tension. And the general idea of this kind of model is that we are able, by the erasing structure mechanism, to elevate the tension of sigma 8, and if we have something else, something dark radiation, number of effective degrees of freedom free, or something like that, we can more or less say something about the H naught, but it's not perfect. And I think that's all, so thank you.
Thank you. Thanks for being on time. So, yeah, there's one question here.
Thank you for the talk. First, I wanted to ask if you can think of dark energy as a field where your particles experience friction when traveling through it.
Yeah.
Okay. Then another question. You introduced some non-conservation of stress energy tensor, but this means that your dark energy is now at some dynamical field or dynamical something. But lambda CDM, lambda there is just a cosmological constant. So what model of dark energy
you can just parameterize dark energy with the double B cold dark matter, and that's all. We are not entering in the, let's say, the very fundamental description of dark energy. This is as you do with the Thomson scattering. You don't need the perfect description, particle description of Thomson scattering to just put in your equation, in your cosmological equation. So here is the same. We don't care about particularities of dark energy, but we just parameterize dark energy, whatever it is, in a double B cold dark matter parameterization for the equation of state, and that's all. We don't care about the particular thing of dark energy.
Mm-hmm. Thank you.
All right, so hi everyone. Welcome to this presentation. My name is Francesco Sinigaglia. I'm PhD student jointly here at the IAC in Tenerife and at the University of Padova in Italy. I work in galaxy evolution and in cosmology and large-scale structure. And today I will talk about our first detection of H1 galaxy scaling relation beyond the local universe with the Miércoles telescope and why this is relevant in galaxy evolution, in cosmology, and in other fields. So the scientific rationale is fairly simple. As in every field of physics, we want to measure a scaling relation linking different quantities. In this case, these quantities are properties of galaxies. So in principle, gas mass, stellar mass, time formation rate, and could be others. It's very important to know about scaling relation of neutral hydrogen because it's essentially the quantity that forms molecular hydrogen, which in turn forms stars. So it's of course in galaxy evolution is very important. Here on the left panel you can see existing constraints on the H1 mass versus stellar mass relation in galaxies in the local universe. And this before August this year was the only constraints we had on this kind of objects. Here on the right is a picture showing the real H1 contours in galaxies compared to the optical disk, just to show how large it is compared to the optical disk. And this is very important, for instance, also in the field of particle physics, since the disk is much more extended of the H1 disk and permits to probe rotation of galaxies way beyond the optical disk, so the disk formed by stars. Okay, so how can we trace H1? Can be traced in absorption, how we saw in the lectures of these days, as well as in emission. We cannot do that in absorption at low redshift because the Earth atmosphere is opaque to the UV radiation. So we have to resort to the 21 centimeter emission line. 21 centimeter is in the radio domain, in the rest frame, and goes even to lower frequency as we go further in redshift. The problem with this is that the 21 centimeter line is very faint. So this means that we can typically detect a sample of galaxies in the local universe, but this cannot be done at higher redshift. So at higher redshift, we cannot detect a statistically significant sample of galaxies. And therefore, we need to resort to other technique. Spectral stacking is one of these. It's very simple. One starts with the individually undetected spectra, shift them to the rest frame, and coadd them. And since the signal grows linearly with the number of spectra and the noise with the square root of the number of spectra, then if one divides the two quantities, one can get the signal-to-noise ratio growing as the square root of the number of spectra. And in the end, ones end up with something magical like this. The data I made use of come from this survey, the MIGHTY survey, which was conducted with the Miércoles telescope, which is the precursor of the SKA. Made of 64 dishes, 13.5 meter across, located in the Karoo Desert in South Africa, and surveying the H1 emission over this bandwidth, which corresponds in redshift from 0 to 0.5. Here we have observation over 2 square degrees, which is small for cosmology, but fair enough for galaxy evolution. Okay, so coming to the results, we considered a sample of 9,023 galaxies, star-forming galaxies, which roughly speaking are blue, H1-rich spiral galaxies. Okay, and we, in a redshift range between 0.23 and 0.49, and we stacked all of them together, getting a median redshift of 0.37. Here you can see the global spectrum as a blue solid line, and as an orange solid line, the kind of noise control spectrum that gives you what is the null hypothesis, statistically speaking. So this yields to this gray shaded area, which tells you what is the 1 sigma level, and therefore we can compute the statistical significance to be 7.5 sigma. Okay, this was already obtained in the past. What we did new was to split the full sample into subsamples in stellar mass and to compute separately the H1 mass for all of these three, obtaining 5 sigma significant for all of them, and being able to build for the first time this kind of scaling relation beyond the local universe. Here our data points are the red squares, the linear fit, the dashed red line is the linear fit to our data in log scale, so it's actually a power law. And we compare that to existing constraints in the local universe, which is this blue line. And we also overlapped the results from hydrodynamical simulations here at redshift 0 as a green dotted line, and at redshift 0.4 as an orange dashed dotted line. So yeah, this is the first detection ever of this kind of objects, which is important for various reasons. We see that there is a good agreement with cosmological simulation. You might argue, okay, yeah, within a huge scatter, that's true, but it's still something. And if one goes and computes the time scale on which the H1 and the gas depletion time occurs on galaxies, then it turns out that one needs an efficient H1 replenishment mechanism of H1 inside galaxies over the last 5 giga years, which is more or less the difference in time between the red and the blue constraints we have here. And this might be in turn related to process of minor mergers or cosmological accretion of gas onto galaxies, so something very exciting. Coming to the very end, this connects with two fields we have been talking about in this school. So in cosmology, we can use this kind of constraints to derive the H1 mass function, to compute the total H1 density parameter, the omega H1, and do other things, like for instance, also do prediction and mock simulation of H1 intensity mapping, something we are working here at IAC, for instance. And this is also interesting for astroparticle physics, as I was telling you before. H1 is a better tracer than rotation and of dynamics than stars. Okay, so that's all. Thank you.
Thank you, Francesco. So actually, Francesco finished slightly earlier, which is great. So we might have time for 2 questions. So.
So Francesco, the scatter that you show is the scatter of the cosmological simulations, right? The data,
Yes.
this error bar is just statistical, the error bars of the data points.
Yeah, it's statistical, and so it's computed with a jackknife technique, and it's a bit controversial because it's kind of known that the jackknife error produce an underestimate of the error bar on data, and although
but by 30%, not by a factor 10, let's say.
Yeah, but still, if one, for instance, compare to the same relation to at redshift 0, one clearly see that it's an underestimation of the error bar. But yet it's statistically robust, so everybody uses that, but it's still a controversial point in this kind of analysis.
So my point is that you can also tell the simulators, like the Simba people, I got these, which are among your thousands of simulations that they run this at CCA, which are those that are passing through these points, which physical parameters for the feedback do you have? Can we constrain feedback, right?
Yeah,
because it's really remarkable, well measured, your trend, I would say.
Yeah. And this is something we are actually doing right now. So this is done with the 1 megaparsec cube box. The Simba is available also in a smaller volume with 50 megaparsec cube boxes with all the different feedback models. So it's something I'm doing directly right now. So trying to see what is the difference in this. But yeah, I must say that it's already a relief to see that all those simulations which have been used to do all this kind of modeling of H1 intensity mapping, etc., kind of agree with data. There were not this data before, so a posteriori we discovered they agree. So it's good news.
Next speaker, please.
A ti.
Hello. Hello. Mic check. Okay. Am I audible? Maybe here. Yes. Okay, cool. Hi, everyone. Good evening. My name is Jasbir Singh. I'm a third and final year PhD student at University of Trieste, and I'm working with my supervisors Pierluigi Monaco and Professor Jonathan Tan. And the topic of my PhD is the origin of supermassive black holes in the early universe. So let's go right in. So with the introduction. Now, some of you, or most of you in this room must be aware that we have a pretty good understanding of how stellar mass black holes form, but it's not the same with supermassive black holes. The problem is that these black holes, supermassive, they are more than 10 power 5 solar masses. That's how they are defined. And so the problem comes that at very high redshift, at 7.5, we have seen very bright quasars, which imply that the black holes which are powering them should be more than 10 power 9 solar masses. So if we have a theory which forms these black holes at very high redshift, and if they use some seed stars, and if these stars are like a few solar masses or a few hundreds of solar masses, then there's not enough time for them to grow through just accretion or mergers and then grow up to this massive and then explain these supermassive black holes. Now, there are some theories, but they can explain the masses, but not the number density which we observe, and there are some theories which can explain the number density, but not the mass. So here I'll talk about one theory which can do both. So what I'll consider is, as the seeds of these black holes would be population 3.1 stars, and these stars are basically population 3 stars, but with the additional condition that when these stars are forming at high redshift in dark matter halos, they are isolated from all the other sources, astrophysical sources, which can give some radiation and disrupt the accretion flow. So a quick animation to show that. If I have a star in a pristine environment forming without any other star nearby, this would be considered a population 3.1 star. Now, if there is another one forming nearby, but it happens to be within the feedback distance of the first star, then the second star would be a population 3.2 star or even a population 2 star, depending on the distance from the initial. So this is a population 3.1 or 3.2. But what happens if there's another star forming here? Now, this is clearly farther away than both of them, and so this would be a population 3.1 again. So in our theory, we use this feedback radius as our isolation distance, and what we want to say is that all the halos, if they are isolated by this isolation sphere with d-iso, the isolation parameter, they would be seeded with supermassive black holes, pop 3.1 stars, which will then eventually turn into supermassive black holes. Now, it has been shown that with these population 3.1 stars, which are at the center of the dark matter halo, these stars have an initial mass function which can go up to 100, peaks at 100 solar mass, but can even reach up to 10 power 3. Now, this is already quite massive, but it's not massive enough for them to be around 10 power 5, and then when they collapse, they could be supermassive black holes. So we want something more. So we can take advantage of the fact that since these stars, pop 3.1 stars, are forming inside dark matter halos, so which means that there are plenty of dark matter particles going around. So if we assume that dark matter particles are winds, then if they are self-annihilating within the stars, then this additional energy can be captured, which can allow the star to remain become large in a relatively cool state, so that the ionizing feedback is minimum going outside, so the star can keep on accreting more and more matter. In principle, it can accrete almost the entire content of its natal mini-halo, which could be around 10 power 5. So these stars can grow up to this massive, and when these stars collapse, they would be in the regime of supermassive black holes. So since they're already this massive and these form at high redshift, then there's plenty of time for them to grow 10 power 9, 10 power 10. So quickly going to the methods which I use to apply the seeding mechanism in the cosmological simulation. So I use the code Pinocchio, which is a Lagrangian perturbation theory based code for dark matter particles. And using this code can uses only dark matter particles and then evolves them in a big cosmological box. The one I used is 60 megaparsec. And using this box, it can find out where all the dark matter halos are forming. And what I do is I try to find whenever a dark matter halo is forming, if it's isolated from other dark matter halos with the isolation distance, which I mentioned before, then that halo would be seeded with a pop 3.1 star. So using this algorithm, I will quickly talk about the results which I get. So here I show the co-moving number density of the pop 3.1 seeds, and which eventually turn into black hole. So for different values of the isolation parameter, this is in proper unit. So we can see that most of the seeds formed quite early in the universe, up to redshift 25, and then we can follow their evolution. And this black line is based on an estimate on the observed number density of black holes. So we can see that for a certain range of our parameter isolation distance, our model can explain the observed number density. One peculiar thing about our model is that most of the seeds formed quite early in the universe, I just mentioned. So, which is contrast in comparison to something called an HMT, the halo mass threshold model, which are basically what in many hydrodynamical simulations, if a halo becomes more massive than a certain threshold mass, it will be seeded. So here, this green dashed line shows the case when if you're using something like an Illustris-based simulation, which they seed all the halos with this more massive than this. So the number density rises quite sharply, but quite late in the universe. So there's a big difference in the number density at higher redshift. Now we can also look at the occupation fraction which we get. So the top row shows for in the log scale, and the bottom is in the linear scale. So for 3 different isolation distances, different redshifts. So what we can take away from this is that at 0 redshift, most of the halos at the higher mass end is always occupied by black holes, since the occupation fraction always goes up to 1. Also, we can also take a look at the clustering. Since there's not enough time, I can just tell that we see that all the seeded halos, they show lower clustering compared to all the halos which have same mass or number distribution, and which could be a potentially observable signal. So here the blue line corresponds to the seeded halos, and the red one corresponds to halos with the same mass and number density, and it's always lower. So I also mentioned that we have the number density at the early universe is quite high compared to the HMT model. So we can exploit that fact by looking at the Hubble Ultra Deep Field. And if we try to count the number of EGN sources in the field at high redshift, then we can basically try to constrain our model for different isolation distances and even for the HMT model. So here I try to create synthetic ultra deep field, and for different redshift bins, we can see that at higher redshift there's a very big difference in the number of sources which could be observed in a field. Finally, we can also calculate the merger event rate, and this could be used for predicting the upcoming PT experiments such as NanoGrav or the upcoming LISA. And we can estimate the merger event rate per year. And probably the LISA people won't be very happy with the merger rate because it's quite low, but it is what it is. So, and I'll leave with my summary and conclusions. Thank you.
Thank you. Thank you, Jasbir. So, question for Jasbir?
Do you need any? What are the requirements on the dark matter actually? So what when you say wind dark matter, there are some constraints on this.
Yeah. So what the research has been done in the papers I showed before, they are considering winds of mass around few hundred GeVs, and then they also using this range they are able to show that the energy which could be released, given the fact that the stars are at the center of a halo where the number density is the highest. If the mass of the particles is around few hundred GeVs, then the energy would be sufficient for these stars to capture most of the energy, and then they can grow. And this could actually be reversed, and then we can also have different mass of the particle, and then we can actually constrain the mass and the cross section area with this.
Hello, I heard that there is a problem where people don't understand very well when supermassive black holes appear in cosmic evolution, and I wanted to ask you about this, whether you can say something about that.
Like in what sense they're hard to appear?
Actually, this was an argument used by Fulvio Melia in favor of his CT model, saying that with his CT model, there was no problem with supermassive black holes emerging at a particular redshift. But I don't know much about this subject, and I was interested whether you could model this and whether you found no disagreement with observations and so on.
From what I understand, there are many theories which are able to explain this
these high redshift quasars, which are very massive. And there's a direct collapse method. Then this can explain those high massive black holes. But the problem is that they cannot explain the entire population, which we would expect at redshift 0. So our model can explain the entire population.
Thank you. Yes, we have to move on. Is Biraj Nistane.
Hello. Yep. Hello, everyone. My name is Viraj Nistane. I'm a PhD student at the University of Geneva with Professor Martin Kunz. And today I will be talking about my some of the existing and my ongoing work on cosmological forecast using 21 centimeter intensity mapping with the upcoming radio telescopic experiment called HIRAX, which stands for Hydrogen Intensity Mapping and Real-Time Analysis Experiment. So for the introduction, I will just quickly have a recap over what we have learned during the lectures. So we have the major constituent of our universe, which is the dark energy. And one of the many probes to measure dark energy is called baryon acoustic oscillation, which are basically the imprints of the acoustic oscillation from the primordial plasma. And these oscillations are apparent in the careful survey of galaxies as a slight bump in the correlation function of the galaxies. And these can be also translated to ripples in the galaxy or matter power spectra. So there is another method to trace the matter distribution in the universe, which is via the neutral hydrogen, via observing the 21 centimeter emission from neutral hydrogen present in the universe. It is present in abundance in the galaxies and intergalactic medium. And so what the 21 centimeter emission is basically the radiation due to hyperfine splitting of the 1s ground state of hydrogen atom. And what we observe is basically the redshifted 21 centimeter line. Now, what we want to observe is the sound wave imprint from recombination, which is quite large, which is a quite large scale, which is around 150 megaparsec scale, and that requires a large volume. And counting individual galaxies and going up to a high redshift may be challenging in this case. So we basically ignore spatial resolution, and we use the technique called intensity mapping, through which we can obtain the redshift information, and we finally use the BAO peak as a standard ruler for charting the expansion history. So now there are some challenges with the detection of 21 centimeter signal because it's a weak signal and the foregrounds are high, we require large volume, etc., etc. So this has also been covered in the lectures on large scale structure. So the experiment HIRAX is to be built considering these challenges in mind, and it's a compact array of 1,020. It is to be a compact array of 1,024 dishes, operating at 400 to 800 megahertz, and currently the 256 array has been funded, so it will be located at the Karoo site, the same site as SKA in South Africa. And the dishes are stationary, but they can tilt for more sky coverage. So going through some existing forecasts, so we set some basic limitations on the K perpendicular, K parallel modes, the limits on K parallel, K perpendicular based on the angular coverage and the frequency coverage of the experiment. And keeping these in mind, we have some Fisher forecasts for the power spectrum errors. These errors can be translated into the errors on length scale. And so this plot on the lower right is mainly to show the comparison between the recent EBOS measurements. And you can see that the HIRAX 1024 survey can constrain the length scale at a percent level out to a high redshift. So that is what is expected out of Fisher forecast at least. Then these constraints, the power spectrum errors, can be translated into cosmological constraints going via distance parameters. And the main thing to note here is the high figure of merit, which is approaching the stage 4 class galaxy surveys, having a figure of merit about 400. So now my contribution comes in, and basically I want to compare this Fisher forecast with using a more sophisticated approach using end-to-end cosmology simulations, which are capable of incorporating computer simulated beams, so with the full structure of the beams. And once the power spectrum errors are obtained from these simulations, the so-called M-mode simulations, we can do MCMC analysis to constrain both the distance and the growth parameters, as well as the cosmological parameters, and eventually the dark energy equation of state parameters. So here are some of the results for the 4 frequency bins that we consider in the simulations. And so what I've shown here is just the power spectrum errors distributed along k perpendicular and k parallel shapes. And so I will select one of this subplot, which corresponds to 500 to 600 megahertz around redshift 1. And what we see here is the 1D representation of the same thing. And on the upper plot, we have the representation for the whole k range, while I select some of the k bins in the lower plot to just avoid the nonlinearities and the foregrounds on the lower and upper side of k range. And the blue plot here corresponds to one of the power spectrum estimator available in the M-mode estimator, M-mode simulation, sorry. And the orange one corresponds to another type of estimator called unwindowed one, which is also via MCMC, via the simulations. And both are compared with Fisher forecasts, which is the black curve. Now, these can be translated into some distance parameters and the growth parameter constraints. And finally, we can also obtain independently the constraints on cosmological parameters. So the left-hand side is using only the partial shape of the power spectrum, while the right-hand side, which is in bit dark, it's using the full shape analysis of the power spectrum. And that is going to be also a new contribution in this project. And one of the next steps is to add Planck priors to effectively compare my contributing results with the already existing Fisher forecasts for the dark energy equation of state parameters. To conclude, I would just like to highlight the high figure of merit obtained from the Fisher forecast, the existence of a sophisticated approach using M-mode simulations to compare with the Fisher forecast, and we can also compare different beam configurations, different power spectrum estimators, and different pointings on the sky using the M-mode simulations. Thank you very much.
Thank you, Virag, for being on time. Question for Virag?
If you compare your results in WA versus W0 with the supernovae, your error bar are bigger.
So this is
because this is your results, but if you compare, for example, with the same results obtaining for supernova.
Yeah, well, so this won't be, I wouldn't say these are the final results. Sorry?
So the scale in WA is so large in size.
It is, yeah, but that's also the Fisher forecast. So I would, for the Fisher one, I would recommend you to see this one, which is.
No, but the interesting is if you show just your results. Because if you joined your results with another cosmological probes, of course you are going to decrease the uncertainties.
Right.
Yeah, but.
Yeah, I mean, I would say for now we aren't focusing on how tight the constraint should be, but just on comparing or effectively verifying the Fisher forecast results using M-mode simulations available in the HIRAX pipeline.
But this is very interesting that it is a new cosmological probe.
Yeah, I mean, it's the work is in preparation, so I wouldn't say wouldn't give too much attention on these results. Yeah.
Well, Virag. Thanks a lot. So we switch to the next speaker.
Thank you very much.
Can you hear me? Okay. Hi everybody, I'm Raul Gonzalez Gonzalez. I'm from IAC, the University of La Laguna, and I will speak about measuring the polarization on CME with the Quixote and LightBear. So, following the Big Bang and inflation theory, two kinds of waves was being generated: the density waves and gravitational waves. And in the meantime, the light traveling in space and with space was trapped in the primordial plasma, and because of the scattering with the electrons, until reach the last scattering surfaces, and at that moment they should present the characteristic polarization pattern that it was imprinted by both the waves, but only the gravitational waves imprinted the characteristic signal for the B modes. And until now, B modes has not been yet observed. So to observe it will be a strong proof of the inflationary theory. So many missions, so 3 missions had been observing the CMB, COBE, WMAP, and Planck, but with different levels of sensitivity and precision. But none of them was enough precision to observe the B mode. So in the next feature, in 29, there will be launched the LightBear space mission that is led by the JAXA, the Japanese space the agency. And I'm part of this mission, so I will show something about it at the end of the presentation. So we can measure the polarization of CMB the same with as the same way we can do for the light, but we need the Stokes parameters to quantify the polarization of the light. So the Q parameters will give us the polarization horizontal and vertical, and the U parameter give us the plus and minus 45 polarization. We can combine these two parameters and develop it in spherical harmonics, and to express it in terms of E modes and B modes. And these are the two patterns for the B modes. And this is the way in which we are trying to discover to manage with this. But we have a problem that the B modes are very faint, and we have a lot of contaminant radiations that we call foreground. The principal ones are the synchrotron, the free, the thermal dust, and the anomalous microwave emission. So in the left panel, we can see an intensity plot, and the right panel, we can see a polarization plot. And as you can see, the CMB, the signal from CMB, is always under the foreground. So we have the problem that we have to know very well these kinds of radiations, because we have to subtract it from the signal to stay with the CMB signal. And these are the mathematical model that through which we are describing each radiation. You can see here the AMI, the yellow line is the AMI. The AMI was discovered 25 years ago, more or less, and this it seemed not to be polarized, but it's still under investigation. And this is the focus of the part of my work. So this is the same thing, but for the B modes. You can see the blue line are the B modes as a function of the tensor to scalar ratio, and these stripes are from the foreground. So you can see that, and this is the upper limit at the moment for the tensor to scalar ratio. So you can see that more or less always the B modes are always under the foreground signal. So what are we doing here in the Teide Observatory? This is the place where this is placed our instrumentation. We have four experiments: Quixote, Quixote, groundbed that is in phase of calibration, TMS that will start next year, that is a spectrometer, Rebel already spoke about yesterday, and the STRIP that is an Italian experiment that we start in the next future. This is Quixote. We have Quixote 1 and Quixote 2. I will go very fast here. This is it has a Cosdagron design, an aperture of 2.25 meter for the primary and 1.9 meter for the secondary. Quixote observed in 4 frequency with 4 horns. The frequency are 11, 13, 17, and 19 gigahertz with this angular resolution and this sensitivity. And it started to observe on 12, and it finished at 18. Next year, at the beginning of next year, we will replace the MFI, the first instrument in Quixote 1, with the MFI 2, that is an upgrade of the multi-frequency instrument, and that will be a better sensitivity of the previous one. In Quixote 2, we have the 3040 gigahertz instrument that will serve at 30 gigahertz and 40 gigahertz with this angular resolution and this sensitivity. It will start. It is started on 21, and it is also in phase of calibration. I'm also part of this work. Coming back to the previous plot, this is the range, the frequency range in which MFI and TFGI are working. So, okay, the phase 1, the two principal objective in the phase 1 was to characterize very well the synchrotron and the anomalous microwave emission. And during the second phase, the aim will be to put together the work from Quixote and from Groundbird to reach a level of sensitivity to find the tensor to scalar ratio until reach the level of 0.01. And this was what MFI did in his work. He did a wide survey mostly for ground study, a deep cosmological survey to study the B modes until around 18, and a galactic regions to study the foregrounds and in those regions. This is just some maps from EQ and U for the wide survey. Anomalous microwave emission is part of my work, and the aim of this work is to measure the polarization and upper limits, or to improve it for the EMI radiation in some galactic region. We selected 3 regions because they are the most bright and the brightest, and the best to the region. So they are Rho Fuci, W42, and Perseus. I put as an example what I did in Rho Fuci. We have 3 maps: the intensity, the Q and U Stokes parameter for the full frequency. This is the region I selected to do the aperture photometry to produce the spectral energy distribution. So these are the 4 points for Quixote. You can see the importance of Quixote to characterize the AMI. This is the cure for AMI. This is the cure for the free, and this is the cure for it doesn't see very well, but anyway, here there is the cure for thermal dust, and this is the fitting parameter. So this is the AMI, the peak frequency of the AMI, and the width of the AMI. These are these fitting parameters come from an MCMC fitting. We can, thanks to this, we can have the AMI, the Q, the U, and the polarization, and the fraction of the polarization of the AMI. These are the parameters that is important for us to understand how is the upper limit of the polarization. Here we are not so in the Quixote frequency. We are not so stringent, but okay, and we are more stringent for in other frequency. So this is the work from Matteo. You can see the details. This is the study of the AMI variation along the galactic plane. You can see the details in the poster for Matteo. This is a list of our publication. Some of them are already published. This is the publication from Matteo. This is mine. And the last slide. As I told, I am a member of the simulation of infrared calibration group from Lightbird. Lightbird is a collaboration of many institutions. Over 300 researchers from Japan, North America, and Europe are working on it. It will survive for 3 years from the L2 Lagrangian point, and will cover with 15 bands this range. This should be the definitive search for B-mode signal for cosmic inflation in CMB polarization, and will be make or a discovery or rule out some well-motivated inflationary model. And the aim is to reach the level of sensitivity. This is the map I created. This is a simulation of some celestial object as observed by Lightbear, and so this is how Lightbear observed. It's a little bit complicated to explain if you want, I can explain later. So that's all. Thank you for your attention.
So, questions for Raúl? Marcos.
Thank you, Raúl. I mean, this is not the first talk about Quixote that I see, and it's all about foregrounds and how we can remove them and then make like an amazing measurement of the B modes. But I guess there's also information in these foregrounds, right? Something that we can learn from. Like they are not just, you know, like some shadow that we cannot get anything. Like what can we learn from these foregrounds? Like any kind of physical parameters or anything?
Yeah, I had the time to put this inside because I prefer to give an overview. Maybe some of you already know something about Quixote, but maybe some of you doesn't know anything, and maybe nobody know about what is our aim, what Quixote is doing. So I prefer to focus on a general aspect about what we are doing. About the foregrounds, we are focused in the low energy foreground, so synchrotron and AMI. There are, as I show you here, we have a lot of publication about the synchrotron. In the case of the AMI, also we are publishing some papers. The paper from Matteo is one of them. Mine is one of them. And about the AMI, we are trying to understand what is the AMI. AMI seems to be very strong correlated with the thermal dust. So it seems that come from the is an emission that comes from the thermal dust, and it seems correlated with the velocity of the rotation of the thermal dust grains, and there are 2 or 3 models, models that we are try to understand in which way the AMI is working. The most probable is related to the electric dipole of the grains of the dust that rotating emit this kind of radiation. Another possibility is that they have a magnetic dipole. They interact with the magnetic field and emit this kind of radiation. But in this last case, we expect a very high polarization. But all our measure give us a very low polarization. So it is the reason why we are trying to discharge the last one, and the most probable hypothesis is that the AMI is related to the grains, the powder grains rotating.
Okay. Thank you very much, Raúl. And also thank you to all the speakers. Very good talks. I'm impressed. Also impressed with the timing. It's been spectacular. I also want to thank the lecturers who have also attended the lectures and the talks. And yes, so thank you to all of you. I'll see you tomorrow.